Hello everyone, I am Juan Herrera, and I am going to present this work entitled Privacy-Aware and Context-Sensitive Access Control for Opportunistic Data Sharing, authored by Soyon Chen, Javier Berrocal, Juan Manuel Murillo, Christine Julian, and myself, and presented to the Secure IoT, Edge, and Cloud Systems workshop in the CCGrid 2021 conference. So we find that smartphones are some of the most used devices in the world. In developed countries, we have up to 80% of penetration rate in smartphones. And these devices have something quite interesting. They have sensors that allow us to know a user's location, how they are moving, their sound level, the weather in the zone they're at, their temperature, etc. Therefore, it can be used to build the context of a person. This is very useful for what is known as context-sensitive applications or context-aware applications that are able to offer relevant information or services to the users, but can also be kind of dangerous because through context, it is possible to trace one person or to know exactly where they are, to know their habits, etc. So for this reason, we find that some of these contextual applications or context-aware applications are being pushed to the opportunistic space through opportunistic data sharing. The idea is that each of these users that is running a context-aware application on their phone are going to connect with each other and share contextual information with each other, but they are going to do it in a certain way, which is opportunistic. This means that there is no underlying network like a mobile network or connection to the internet overall. They are going to connect using the opportunistic network that is created between them using wireless technologies such as Bluetooth or an ad hoc Wi-Fi network, etc. And this kind of opportunistic solution has quite a few benefits if we go to context-aware applications, because it allows every user to contain the context within their phones, and therefore they don't have to completely release it. They can only release it through these opportunistic data sharing communications. Now, however, we find that we often do not want to share all of our information with every single other person simply because we're sharing it opportunistically. We normally want to put some limitations over it. And sometimes each user will want to have different limitations. First, on who can access the data, but also on how much data of theirs can be accessed. Moreover, while in cloud systems or decentralized systems, we find that every single user is known before making the access request, and therefore we can authenticate users knowing who they are. In these opportunistic situations, we are based on the context to authenticate a person because we may allow a stranger to access our data. For instance, if we are in an emergency, maybe we can share our context so they know where we are to find help, etc. We need a context sensitive because we're using context to authenticate. We need to be privacy aware because we need to control how much information is accessed, and we need to be opportunistic as well. And this work, we present PADEC. PADEC is precisely a solution meant for this kind of scenarios. To better understand what's the motivation behind PADEC and to better understand PADEC overall, we use a case study application. So imagine we have the city. We use New York City as an example, but any city works, in which we have different places that locals enjoy going to, such as parks or restaurants or even monuments of the city. Those are the so-called points of interest or POIs. To boost tourism, we have that the local government releases an application. When locals install this application, they have a history of the points of interest they have been to, so that whenever a tourist with the application comes and connects to these local users, they can know which are the POIs that locals like the best. So essentially, we have a situation like this. We have locals that have their POI histories of all the places they like going to, when they like to go to them, etc. And when some tourists want to know a good bar that is nearby or what is the most visited monument in the city, they can share the data opportunistically, and therefore they can get all the information they need. Of course, this information is also sensitive. It has the visited places that each of the locals have been to and the frequency of visit that they do. So they know how much they visit a place. And of course, with this information, it is fairly easy to track a person down. The opportunistic approach is also preferred in this scenario because of two main things. First, because each user is able to maintain data ownership. This also means that there is no centralized or global entity knowing everything. Now, of course, as we have talked about, we need some access control restrictions, but we cannot set them freely because If we set too restrictive access control conditions, such as only people who I know and I have accepted previously, etc., can access my information, then the application is essentially useless. If I have to approach someone in the street and ask them to allow me to access their POI history, I'm probably better off just asking them what's the nearest bar. On the other hand, if we are too unrestrictive, it is fairly easy for them to track us. So we need to set proper access control measures. And if we allow users to hold their POI history, let's also allow them to define their custom rules for access. So each user can decide who can and who cannot access their information. Of course, we need this access to be granted based on the context, because we are going to allow access to strangers. We also need to release more or less information depending on the consumer's context. And also, each user must keep ownership of the POI history, so it is opportunistic. It is a good scenario to show the possibilities of PADEC. Going ahead with PADEC, we have to build each threat model. Essentially, we find three kinds of threats that we are going to try to address with PADEC. First, we'll have the more general threats such as unauthorized access, which is to grant access to a consumer that shouldn't be granted access. Moreover, we have one more specific to PADEC, which is circumventing context constraints. This means that if I only allow friends who are nearby me to access, and a friend is able to access without being nearby me, they are accessing through identity, but they are circumventing all the rest of contextual attributes. Moreover, going with privacy, we have consumer and provider overexposure. Essentially, these are allowing a consumer or a provider to get more information about the other one that they were initially intended to. In the case of consumer, it is by consuming information from their requests, and in the case of provider, it is providing information with a finer grain than intended. We also have insider attacks, because one person could infer finer grain information than intended by making repeated requests. For instance, if I give, whenever I get a request, 1/3 to that consumer of my POI history, and that 1/3 is random, but repeatedly asking for 1/3 and correlating all the different answers, they could build my whole POI history. Finally, we have classic third-party attacks from networks, such as being able to eavesdrop the communications between a provider and a consumer, and also replaying valid access requests. Next to this description of every threat, we have an icon, and that icon will be used throughout the model to see how we address all the different threats. To start, we have step 0, the most basic step, which is encryption. Originally, PADEC uses clear text communication, which of course means that it is very easy to eavesdrop and to replay. To solve this issue, we have used the Diffie-Hellman system, in which we are sharing a symmetric key through private and public keys, so that we generate on every request a different key that is only used for that request, and then it is discarded. This means that a third party cannot eavesdrop, because if they try to eavesdrop, they will not understand the messages. They are encrypted through this symmetric key, and also that you cannot replay the messages. So because if you were to replay and it worked and you actually got an answer, the answer will be encrypted, so you will not know what the answer means anyways. Moreover, as we will see when we design the protocol, Diffie-Hellman can be piggybacked into the service discovery messages, so you do not have to add additional messages to create this Diffie-Hellman key. Now that we understand that, let's get to the first step, access control. Essentially, we want to tell apart who can access our POI history through an endpoint and who cannot access it. And this can be managed very easily through allow lists. For each endpoint, I have an allow list of which are the users that are allowed to access my endpoint. Of course, this does not scale. If I have a lot of endpoints and I want to allow a user to access all of them, I have to add them to every single allow list. If I want to deny access to a user, I have to remove them from all allow lists. So instead, what we can do is that we can create groups of users, and then the accesses are granted by group. So I add a group called family, and I say that my family can access my POI history. This can be very similar to something, because instead of groups, if we call them roles, we're using some sort of role-based access control, or RBAC. Essentially, this will be the protocols of now. First, we want to discover whether the provider has or does not have the endpoint. We return that availability, and then the application can make a request, send their identity. We check if they have an according role, or if they are in an according group. And if they have the permission to perform that request, the request is performed and they get the results. Of course, this means that now you cannot get unauthorized accesses anymore. But we can still circumvent context constraints. We're only accounting for identity so far, but we consider the full context. There is also an extension that allows us to focus on the whole context instead of only identity, which is attribute-based access control, or ABAC. Through ABAC, essentially, we can use any single attribute in the context to validate a user's main change. Is that instead of sending only our identity, we send all of our context, and it is checked on the provider side whether we are allowed or denied the access. However, sending the full context first is a large overhead because I am sending all of my contextual information, and the consumer doesn't want to send the information because it's private, and the provider does not actually need all that much information. The first novel thing we do with PADEC is that we create keyholes. Whenever we do service discovery, we have the provider advertising which are the contextual attributes that are required. So if I need you to know if you're my friend or if you are nearby, I will tell you to give me your location and your identity. I will not tell you what is the logic behind my access control rule, but I will tell you which contextual attributes you must supply. That is what we call a keyhole. Once you have my keyhole for the endpoint, you can create an appropriate key with the requested attributes, and that is what you send over to me. So essentially, the differences with step 2 is that now instead of just returning an endpoint, we also return the keyhole, and then instead of sending the whole context, we just send the key. This does not fully address consumer overexposure, but of course, the surfaces exposition of consumers is highly reduced. In step 4, we find that some of these access rules can actually be decomposed into multiple rules with smaller keyholes. For instance, as I've said, grant access to people nearby or my friends. I can only validate that with location. For example, if you're nearby, you give me your location, and if you're nearby, you're going to get granted access, or your identity. If you're my friend, knowing that you are my friend, I do not need to know whether you're close or far. So only with location or identity, I can try to validate it. And even if you are wrong on what my logic is, because you don't know the rule logic, you can actually test multiple keyholes to try and see if you can get access through any of them. The decomposition is what we call access levels. So a user is able to decompose their rules into multiple access levels to have multiple keyholes and give more chances to consumers to consume one or another. Essentially, the only difference from what we had before is that now we have multiple keyholes. Of course, that greatly reduces all the surface exposition surface of a consumer, because now they only have to send the information from one of the keyholes of the access levels that have been defined over the endpoint. However, so far we have focused on consumers' privacy, but we also need to focus on providers' privacy, because as we have said, we're going to release final-grade information to friends, course-grade information to strangers. All of my POI history to friends, only the places I've been to last week to strangers, for instance. So one way to do this is that we have different access levels now on each of the endpoints. Now we could attach a filter that is configurable to abstract or obfuscate the resulting output. So we can have an access level requesting for being my friend, an access level requesting for you to be nearby, but each access level has a filter that will tell you how much grain you get on the information you obtain as a result. Of course, these filters might also be idempotent. So as long as my POI history does not change, if you repeatedly query for the same information, you will get the same response. That means that, of course, there is more privacy for the provider, and that prevents any kind of insider attacks, because if you continuously request for the same kind of information, you're guaranteed to get the exact same answer, and therefore you cannot correlate different answers. Anyways, the main difference from what we had earlier is that now every access level has a filter. So after the request is performed, the filter is executed, the information is obfuscated or abstracted, and the results are returned. Finally, we have one final step, step 6, that is multi-access level negotiation. Every time we need to do a request, we have to perform all the protocol, and that is quite inefficient. So instead of performing the full protocol every time, we have a negotiation component. So the consumer can provide a key that fits multiple keyholes instead of just one. So once these consumers are providing keys that fit multiple keyholes, it is the provider's responsibility to test it over every access level, starting from the one with the highest precision, of course. If they get granted access at some level, they get information at that access level. If they are denied access at every single access level, access is effectively denied. This is not reflected in the protocol, but it has an effect, as we will see, in the amount of successful accesses, because now we're going for evaluation. To evaluate our solution, we have simulated using D1 the very same case study we have been talking about in the New York City map. Tourists are going to consume information and move through touristic zones, of course, while locals will move through both touristic and residential zones, providing their POI histories. We actually were obtained from a real dataset from checking news stories from Foursquare. Moreover, each context attribute is ranked to more to less sensitive, so that some tourists might be reluctant to provide some of their context attributes because they feel they are very sensitive and the information they get in exchange is not worth it. In each test, we measure many different metrics, but mainly we have consumer privacy, which is the ranks of the attributes revealed versus the ranks of all the attributes that a consumer has, and provider privacy, which is the obfuscation of their POIs. Starting with the evaluation, we have on the left the privacy from consumer and provider and the number of successful accesses. In step 1, which is essentially RBAC, we find that consumers have some privacy because they only have to reveal their identity. Providers get no privacy at all, and there is no many successful accesses because only people I already know can be validated. Any strangers get denied their accesses. If we get to step 2, then we're using ABAC, we're using the whole context. That means that consumers get no privacy at all, but the number of successful accesses rises. In step 3, we add keyholes and keys, and that means that consumer privacy is enhanced. In step 4, we have added different keyholes and access levels. Of course, that means that a consumer has to test multiple keyholes in order to get access to information, which means that there are less successful accesses, but it has greatly improved the consumer privacy overall. In step 5, we add filters, and essentially the only difference is that now we have a lot of provider privacy because now providers are able to provide different levels of grain depending on who is accessing their information. Finally, in step 6, the final step, we find that there is less consumer privacy because they provide larger keys, essentially, as they fit multiple keyholes, but there is a much higher provider privacy and a much higher rate of successful accesses, as they do not, a consumer doesn't have to test multiple keyholes. In essence, PADEC effectively trades off all of these 3 metrics. If we move on to overhead, we find that in step 1, step 2, the messages are more or less small, and there's only 2 messages per request in RBAC and ABAC. From step 3 onwards, we find very similar sizes, which are essentially double the size of the previous steps. And of course, we have 4 messages per request because we have to do service discovery within the access control protocol. However, this size is not very large. At max is of 1,600 bytes, which is not very important considering the modern wireless communication techniques. So while PADEC doubles the overhead of RBAC or ABAC, it is still very small to begin with. Finally, we get to expressiveness, where we have evaluated the amount of rules one can create with PADEC, the amount of contextual attributes one can use with PADEC, and the amount of access levels that can be created with PADEC versus RBAC and ABAC. Of course, access levels are inherent made in PADEC, so only PADEC can create more than 1 access level. And the number of contextual attributes is the same as ABAC. What we find is that because PADEC allows one to combine the context of consumer and producer to, for instance, know what is the distance between them, one can create more rules with PADEC than with ABAC. On the graph of the right, we find the different access levels, and it is a very graphic way to show that if we are using PADEC, we have a range of colors that have different levels of access, while in RBAC or ABAC, access is either denied or allowed. So overall, PADEC's expressiveness is higher than RBAC and ABAC. So in conclusion, if we want to push context-sensitive applications to the opportunistic space, such as mobile crowd-sensing applications, that means that users can hold ownership over their data. But this also means that users must protect their data. And to protect their data, they need to be a solution to be expressive, they have it to be context-sensitive, they need to be privacy-aware, and also it has to be designed for opportunistic interactions. Essentially, PADEC is what these users could use because it is much more expressive than RBAC or ABAC, and it mitigates all the threat model that we have defined while also being context sensitive and privacy aware. Finally, in the future, we try to address another attack called multi-type insider attack. Instead of correlating many queries to the same endpoint, one could correlate multiple queries to different endpoints that provide different contextual information about the user to, in the end, know more finer-grained information that that user initially wanted to. Thank you very much for your time, and please give me any questions you have.